In this video, I want to show you how to use intensity property to show energy balance problem. Given steam at 170 degrees Celsius and H bar absolute is flowing through a nozzle isothermally. Isothermally simply means the same temperature at the inlet and outlet. And the steam exit at 2 bar absolute. Calculate the heat for the system. Assume the basis is 10 kg per minute at steady state. I put this note so we know that the specific enthalpy at inlet and outlet based on the temperature and the pressure term. You can also find this value at the back of the book. First, let's draw a flowchart based on the problem statement. Assume the basis is 10 kg per minute. That is a mass flow rate, so that's m dot. And the pressure turn and temperature turn are given, and I already found out the specific enthalpy at inlet and outlet. So just label all the variable given based on the problem statement. And we are looking for the heat. Next, write down assumption. What do I assume to achieve the goal? Well, based on the problem statement, it's not given any velocity term and it's not given any elevation change, so we can ignore kinetic energy and potential energy for this problem. And obviously this is a nozzle, so there's no shaft work and no boundary work because there's no molecule crossing in and out of the system that doing work, although there's a mass flow. Then we can also assume that this is a continuous steady state, so nothing changes with time. The value that's shown in the flowchart, they are constant. It doesn't change from time to time at inlet and outlet. Now, based on the problem statement, this is a good example of open system. Obviously, there's mass flow in and flow out continuously at steady state. So this is an open system, continue steady state problem. Then we know that the material balance for open system is input equal to output, and the input is 10 kg per minute for the steam and equal to output, and then we can integrate with one symbol, m dot. The energy balance for open system continuous steady state is change in enthalpy plus change in kinetic energy plus change in potential energy equal to heat plus work. Although we have some terms that cancel out, but it's preferred to write down the whole energy balance equation first, and then we can decide which term to cancel out based on the assumption. Now we say ignore kinetic energy, ignore potential energy, so this term cancel out, and there's no work because the sum of work is the work done by shaft work and boundary work, and then they don't have any work term related to that in this problem statement. So we simply get change in enthalpy is equal to heat flow. And we know that the change in enthalpy is a state function that is final state minus initial state, and this problem is the outlet minus inlet. And the enthalpy is the mass times specific enthalpy. Then substitute the number given in the problem statement into this equation. Then we get change in enthalpy is 423 kJ per minute. And based on the net energy equation we just got previously, then we get heat is the same value as the change in enthalpy. That is 423 kJ per minute. But the problem is asking for heat in kilowatt, and kilowatt is kilojoule per second, so we can convert minute to second by dividing by 60 seconds. Then we have 7.05 kilowatt, and that is the final answer.